welcome. Today is the first day of this week, and I hope so far you found this initial lessons useful. So, what we were looking at in the last class was the conditions to have laser actions. And what we did, we used the principle of detail balance to equate the rate of absorption and rate of emission, and thereby we boil down to a condition where the Einstein's formalism matches with the Planck's one, and from there we got two useful relations. Okay, the ratio of stimulated to spontaneous emission, which says that is equals to 1, stimulated emission to the absorption. So, we found that the rate of stimulated emission is equal to the rate of absorption, and we also saw why it is difficult to achieve laser at higher frequencies. And we ultimately came to the conditions, okay, at which I can or I cannot get a laser action. So, what we found out that the populations of the two states, we are still considering a two level model. So, for the condition where N2 by N1, that is the ratio of the population of atoms at state 2 and state 1 is greater than 1, only then I can have a condition where stimulated emission dominates and I can achieve laser action. So, suppose for time being, let us assume that I can achieve this condition, that is N2 by N1 greater than 1. Okay. So, at this condition, what do I see? What I will see can be shown graphically if I plot the intensity of light as a function of frequency. So, when I have a condition which is equal to this, I have no net gain. Okay. So, whatever be the scale of intensity, okay, that is flat. Now, our concern is at a particular frequency, correct. So, let me put this as nu 1 2 as we have been using. So, here I do not have any kind of amplification. Now, the condition when I have N2 greater than N1, then what I will have, I am putting some number of photons and I am getting number of photons which is much higher. So, when I give say x input and get n number of times of x as output, then I say I have gain. Here also I am giving photon and I am not getting anything out of it when I have this one. So, my income and expenditure both are same, no gain. So, if I come to this particular condition, then what I will say, I have much more photon than I have already used. So, therefore, at that particular frequency where I am using, I will see a net gain. So, this is not any other type of gain, but other it is called optical gain at this particular frequency when we can achieve this condition N2 by N1, all right. Now, mathematically we got it, but how we can get this condition N2 by N1? If I can get that, I can make a laser, not much trouble. Now, what is that is preventing me to have this condition, right? So, if I can do it mathematically, why can't I actually do it? Simply, if I look at the equilibrium population distribution, and if we again look at the Boltzmann statistics, then what do I have? This is equal to right. So, normally what I can see that N2 is very less than N1, and I want N2 to be much higher than N1, correct. N2 should be greater than N1 in order to have laser action. So, suppose I have again two state model, okay, and I have several atoms here, okay. Suppose I have taken total 8 atoms. Now, in the step 1 I come with some photons, okay. So, there are many photons I am sending in, and 2 of these are going from here to here, fine. So, they make a transition here, this one makes a transition here. So, I essentially have this one and these 2 are non-existing here. So, after sending these photons I get this condition. Now, if I can achieve a condition where half of the atoms are in this state and half of the atoms are in the excited state, then that will be something like this. So, I have 1, 2, 3, 4, 1, 2, 3, 4. This is a saturated condition, okay. So, I have so called, so this was initially all molecules are ground state and very few in the excited state. That was my equilibrium condition, that is governed by Boltzmann distribution. Then by putting light, more and more light, I say I can somehow achieve a condition which is like this, where I have equal population in both the states, and I get a condition which is known as saturation. Now, I have to go here, I have, in this case I have N1 less than N2, here I have N1 equals to N2. Now, I need to go to N1 is less than N2, sorry, here I have made a mistake, this should be N2 less than N1, right. So, now I want N2 to be greater than N1. So, I want to actually invert the population. So, this is my equilibrium population distribution, and what I want to invert this population so that now my state 2 contains more number of atoms than state 1, and this is known as population inversion. Right. So, this condition N2 greater than N1 is essentially a population inversion condition. Okay. So, how can I get population inversion? Now, here we will describe in detail that whether or not we can find population inversion in this system, which is essentially a 2-level system. So, can we? So, the question is, can we get population inversion in a 2-level system? So, that is a question and we will try to answer that. Okay. So, we are going to answer that question. So, obviously, we will take the same 2-level model, their rates and all the details. By the way, I think I have missed out one thing here, that we are talking about this A21, B12, B21, these rate constants, they are known as Einstein's coefficient. Okay. I do not remember if I have mentioned this one, but this A and B's, they are known as Einstein coefficient. You will many time come across in the books also, it is written as Einstein's A coefficient, Einstein's B coefficient and so on. So, you should definitely know this one. Okay. So, if I have not mentioned it, so you know now. All right. So, let's go back to our discussion. So, we are still considering this 2-level system, 1, let me call simply as 1 and 2 without bothering about the bracket notation, and N1, N2. Now, in order to answer this question, we will formulate in this way, because we are going to deal with this population of state 2 N2. We have to see how we can make N2 greater than N1, that is our aim is. So, let us see what is the change in population of state 2. Okay. So, from the basic knowledge of kinetics, we can easily get that. So, how do I write that? I write dN2 is function of dt by dt. Now, this N2 is also time dependent. So, when I am shining light, and then as a function of time it evolves, N2 changes. Now, how it is changing? So, how this one is populated? It is populated by absorption process, correct? And how it is depopulated? By the emission process. So, the absorption processes will be will come with positive sign, and the emission processes, emission rates will come with negative signs. So, if I write this one, what do I have? First, absorption. So, B12 N1 into rho. I am not writing that rho within bracket H nu 1 2 anymore for simplicity, minus spontaneous emission A21 N2 minus B21 N2 rho. Okay. So, from previous discussion we already know that this rate, that is absorption rate, is equal to the rate of stimulated emission. So, I have this condition B12 equals to B21. If you remember the previous class, you have already seen this, correct? So, if I take this B12 equals to B21 equal to be something as B, and suppose I write A21 to be just A, then what I get? I get B N1 rho minus A N2 minus B 21 N2 rho. Sorry, I am supposed to remove this one. So, it is B. Okay. So, what I have is B rho N2 minus, sorry, N1 minus N2 minus A N2, correct? Now, this is a differential equation and we need to solve it. So, what are the conditions that we have in our hand so that I can solve this one? So, at time t0, at time t equals to 0, my N2 is equals to 0. We all agree, right? When there is no photon, okay, we start giving the photon at time t. When there is no photon, there is no population of the state 2. So, N2 is 0, and if there are total n number of molecules, and if I call it like n total, then essentially at that time my N1 is equals to n total. ठीक है? So, what I have this, okay. So, I can get this expression. Now, what do I have for N2 is A is the rate constant for spontaneous emission, right. So, A is for spontaneous emission. Spontaneous emission is always there, okay. It does not require any photon or anything. In vacuum, if you keep it, it will emit, because there is a lifetime of the state. It will come back to the ground state by emitting photon, and that is what is spontaneous emission. So, no matter what, spontaneous emission is always there. So, the rate constant is non-zero. So, therefore, I can say A is greater than 0 always. This constant, this condition is there, okay. So, I have here this B rho in total by this one. So, if I let me write it over here. So, from that expression, if I get N2 by N total, that is equal to B rho by A plus right. Now, when A is very less, it comes to something like, so on the other hand, say if I write N1 plus N2, okay. So, it will become approximately when A is very small, right. So, it will be around half, so or less than half. So, the maximum value is half. Now, does it tell you something? We drew the this two levels and we started exciting it, and we got to a condition when we had a saturated condition, right. So, we had a condition like here, if I show, so 4 atoms here, 4 atoms here, and we call that is a saturated. So, here if you have equal population of this state, so essentially N2 by total number of atoms is half, that is maximum possible ratio of N2 by N total. I cannot get more than that. So, essentially when N2 is equal to N2 by, when N2 by N total is equal to half, that means N1 equals to N2, which is essentially this condition. So, because A is always positive, so essentially what I have, this one is always less than half. Okay. So, forget about going to N2 by N1 greater than 1, I have N2 much less than N1 all the time for, so N2 greater than N1, this is not possible for a 2-level system. N2 by N1 greater than 1, this condition is not fulfilled in a 2-level system, or in other words, population inversion is not possible for a 2-level system. This is an important lesson. So, I know that if I have to get a laser, I must fulfill this condition N2 greater than N1, or I must have a population inversion, and after seeing everything I figure out that, well, I cannot achieve a population inversion in a 2-level system. Okay. So, I have answered the question that I have asked a few minutes back. Now, then question is, okay, if not 2-level, whether a 3-level system can give rise to population inversion. Let us look at it. So, let me ask the question. So, question is 2-level system cannot. Now, is a 3-level system capable of having population inversion? So, if I draw a 3-level system, just for clarity, I am drawing in this fashion. Okay, this has nothing to do with the actual energy level picture. So, I have state 1, I have state 2, and I have state 3. Now, what are the possibilities that we have here? We can have absorption as well as emission from this state. I can have spontaneous emission, I can have stimulated emission. Okay. And if I just consider these two systems, it's a fairly 2-level system. So, I know everything about it, what I should know, I have already learnt it. Now, between these 2 levels, what I can have? I am going sequentially. So, I hit the system with light, I shine light, the molecule goes here. So, at that condition either it can come down here or it can come down state 3, all right. So, I can have, so this single headed arrow means there is a spontaneous emission, okay. And from here I can have spontaneous emission, I can have stimulated emission. Now, whether the stimulated emission will dominate over spontaneous emission will tell me whether I can have a laser using 3-level system. Okay. So, let me answer you first that whether this 3-level system can act as a laser, can it give population inversion? Answer is yes, it can under certain conditions. So, what are those conditions? That is, this level 3 which is lying below level 2 must have a lifetime. So, if I write tau 3 as the lifetime of state 3, then tau 3 should be much greater than tau 2. So, in other words, the lifetime of the state 2 is much shorter. So, it is short lived state, whereas this is much long lived, and this kind of state is known as metastable, okay, metastable state. So, my state 3 is a metastable state. So, and also this state 3 should not be a Dirk state. So, it should not be a Dirk state. So, it should be able to emit radiatively. Okay. So, state 3 should not be a Dirk state. So, at this condition I can actually achieve population inversion. How? That we will discuss in the following class. Till then, goodbye and thank you very much.